All right, today we're looking at product rule, which allows us to differentiate a product. Big surprise, right? The name is a good one. It's pretty obvious what this thing does. But the time it can save us in terms of algebra before taking a derivative is awesome. So notice this example function. It looks like it's the product of two separate parts. So I'm going to just kind of, as usual, use some colors to show what's going on here. I'm going to visualize these two parts as f and g, two functions in and of themselves that are being multiplied. You all know that you could re-express y equals by distributing this or using what sometimes is referred to as the FOIL process. You could do that first. You'll get the same answer. But what we're looking at today is applying what's called the product rule for derivatives or for differentiation. So we're going to try to differentiate with respect to x. Okay? So on the left side, we've seen this notation before. We have dy dx. Now, the product rule says we take the derivative of the first. So our first is in that dark red. So the derivative of the first, let's see. 3 times 9 is 27. X, 3 minus 1 is 2. So 27x squared plus the derivative of 4x is just plain old 4. So it's the derivative of the first times the second. So we're going to multiply it by the second part or the second factor as is. So that's negative 2x to the eighth plus 10x to the negative third. Then we have to add this other piece. And that's the first, right? It's the first, see it? The first. So 9x cubed plus 4x times the derivative of the second. So 8 times negative 2 is negative 16. 8 minus 1 is 7, so negative 16x to the seventh. And then we're going to multiply negative 3 times 10. That gives us minus 30x. Negative 3 minus 1 is negative 4. Negative 30x to the negative fourth. And now we have the product finished, the product rule for differentiation finished. Of course, you can simplify, no need to. You'll find in higher levels of calculus, nobody really asks you to simplify unless there's some other application. And so what we're looking for right now is just to apply the product rule to obtain this new function that represents the slope of our original function at any given value of x. Remember, every time we do differentiation, we take a derivative, we're creating or we're establishing a function that with respect to x for now, that describes the slope or the instantaneous rate of change of the original function.